In order for a substance to boil, the IMF must be broken, or the intermolecular forces have to be broken. This means the stronger the intermolecular force, the more energy is going to be required, resulting in a higher boiling point. In order to get a substance to freeze, the intermolecular force has to be strengthened. So the greater the IMF, the higher the freezing point, because the molecules will be attracted to each other more, so they will not require the temperature to be as low for them to freeze, because they'll already want to go together. Surface tension is the resistance of a liquid to an increase in its surface area. The higher the intermolecular force, the greater the surface tension. We can see surface tension in the picture here. It's the attraction between our molecules on the top. There's also attraction between the molecules on the top and within the liquid. Viscosity is a measure of a liquid's resistance to flow. The greater the viscosity, the thicker it is, or the slower it's going to flow. If we look at all these pictures on the top of the four liquids, assuming that the marbles had been dropped at the same time, this last one would have the greatest viscosity, and the first one would have the lowest viscosity. Viscosity depends on how strong the intermolecular forces are and how complex the molecule is. The greater the intermolecular force, the greater the viscosity. The more complex it is, the greater the viscosity. So here we have two forms of pentane. They both have 5 carbons, but the one on the left is more complex than the one on the right, making it harder for the molecules to flow past each other. Capillary action you've seen in graduated cylinders when you get that meniscus, and that's what allows the blood to flow in your capillaries and the water to flow in plants. It's due to cohesive and adhesive forces. Cohesion is the intermolecular forces among the molecules of the liquid. So here we can see cohesion between, if these were water molecules, between the water molecules. And then adhesive forces are between the liquid molecules and their container. So if this was a graduated cylinder, we have adhesion with the red arrows between the water and the glass. We have adhesion with polar molecules in glass because glass has oxygen, silicon dioxide, and that oxygen is attracting the hydrogen in water. Vapor pressure is the pressure of the vapor resulting from evaporation of a liquid above a sample of the liquid. The more molecules you have turning to a gas leads to a higher vapor pressure. So the higher the intermolecular force, the lower the vapor pressure, because not very many molecules will be turning into a gas. So does liquid A or B have a greater intermolecular force? Assuming that flask A and B are at the same temperature. Go ahead and pause the video and restart when you think you have your answer. We have about twice as many molecules as gas in A than in B. This means it must be easier to turn into a gas in flask A. So A must have weaker intermolecular forces. So B has the stronger one. Another kind of chart that you may have to read is a vapor pressure chart with different substances and boiling points. The normal boiling point is at standard pressure. Standard pressure in millimeters of mercury is 760. So you would follow 760 across, and for pentane, its normal boiling point would be about 38, 36 degrees. Following it over to tetrachloromethane, and it says it's 76. And then water's normal boiling point, 100. Remember, the greater the boiling point, the greater the intermolecular force. So water must have the greatest intermolecular force out of these three. If we change the vapor pressure, let's say 400, now it's going to boil at this temperature, this one, and this one. So around 80, 58, and 28. So go ahead and pause the video and answer these two questions. The lowest IMF will have the lowest boiling point at any given pressure. Chloroform has the lowest boiling point. So chloroform has the lowest IMF. The normal boiling point of ethanol, we're going to find ethanol. And since it's kPa, we're going to find 101.3. And that's pretty close to 80, so about 79 degrees Celsius. Go ahead and pause the video and rank these in order of increasing boiling points. So what you have to do is first figure out which type of intermolecular force is in each of these. We have ionic. We have London dispersion, because it's nonpolar. This is a polar molecule, but it's not hydrogen bonded, so it's dipole-dipole. HF is hydrogen bonded. And neon is also nonpolar, so London dispersion. The lowest boiling point should be the lowest IMF. The lowest IMF is London dispersion usually. And out of helium or neon, we have to decide which one is the lowest. If you recall from part 1 of the video series, we said that London dispersion forces increase with an increase of electrons because it becomes more polarizable. So because hydrogen has less electrons, it would have the lower IMF. Then neon. Dipole-dipole is the next one because hydrogen bonding is stronger than dipole-dipole, and ionic should be the highest. Go ahead and pause the video and restart when you have your answer. So first off, these all have London dispersion forces. Since they all have London dispersion forces, remember the more electrons it has, the stronger the IMF. Since we want the most viscous, we want the one that has the highest IMF. C6H6 has the most electrons, and so it has the greatest London dispersion force. Go ahead and pause the video and restart when you have this answer. So H2O is hydrogen bonded. HI is dipole-dipole. HF is also hydrogen bonded. And HBr is dipole-dipole. So if we're looking for the highest boiling point, we're looking for the highest IMF. So C and D are out. But both A and B have hydrogen bonding. To figure out which one has the greatest hydrogen bonding force, we're going to look at which one can undergo the most hydrogen bonds. H2O can undergo 2 hydrogen bonds because it has 2 sets of lone pairs on oxygen and our 2 hydrogens. While HF, because it's such a small molecule, can only undergo 1 hydrogen bond on fluorine. Even though fluorine has 3 lone pairs, it can't fit 3 hydrogen bonds in here because they'd be too close together. So the answer is A.